These are the notes for AP Calculus on the topic of infinite geometric series. And we're going to first take a look at some more examples of where we're trying to find the first three partial sums and state where the series converges or diverges. And if the series converges, find its sum. So notice here, the starting number here can be really any whole number. It happens to be 0 here instead of 1. 0 and 1 are the two most common ones, but it can really be any whole number there. And notice again, it's infinite, it goes on to infinity. So another way of looking at this, first three partial sums, let's take a look, because in this case, it would be easier to see what the common ratio is. It's not always as obvious as those previous two examples. So if you want the first term, which we call a sub 1, you always plug in the starting number. In this case, 0, so that'd be 3 into the formula for the nth term. Sometimes this part of the formula is called a sub n, because it gives you the formula for any of the terms in the series. So if we substitute 1 there, notice that'd be 3 squared over 5 to the first, which would give you 9/5. So before we find the first three partial sums, let's just take a look at these, because it'll be easier if you, if it's not obvious what the common ratio is, like some of them are, it's easier if you just find the terms first to see what the common ratio is. So there's our first term. The second term, we plug in, the next integer would be, oops, I'm sorry, that made a mistake on the first one there. I accidentally plugged in 1, when actually I should have been plugging in 0. So, mistake there. So when you plug in 0, I looked at the 1 here, but the starting number is 0. So you plug in, it would be 3 to the first over 5 to the 0. When you plug in 0, the starting number, and 3 to the first is 3, over 5 to the 0 is 1, so the first term is actually just 3. And then the second term, now we plug in the next integer after the starting number is 1. So here's where we get 3 squared over 5 to the first. So that's where you get 9/5 is your second term. And then the third term, once you get the first three, you can find the first three partial sums, and you'll also be able to see what the pattern is to find the common ratio. Now we plug in the next integer, which is 2. So it'd be 3, 2 plus 1 gives you 3 over 5 squared. 3 cubed is 27 over 25. So now, before I write down the first three partial sums, let's look at these three. Here's the first three terms here. We've got 3, 9/5, and 27/25. So to go from 3 to 9/5, and then 9/5 to 27/5, now you multiply the numerator by 3 and the denominator by 5. So the common ratio here is 3 over 5, and that is between -1 and 1. So because of that, this series converges. And then we can get the first three partial sums. So the first partial sum is just the first term, which is 3. The second partial sum is the sum of the first two terms. So it's 3 plus 9/5. Get a common number, multiply by 5. That's 15/5. It's the same as 3 plus 9/5. Gives you 24/5. So that's your second partial sum. And then the third partial sum is the sum of the first three terms. So 3 plus 9/5 plus 27/25. So now we get a common number of 25. We already know 3 plus 9/5 is 24 over 25. So if you multiply that by 5 on the numerator number, 24 times 5, well, 25 times 5 is 125. So it's 5 less than that, so 120 over 25 plus 27 over 25. So the third partial sum is 147 over 25. And then finally, since it does converge, basically these sums here, what they're getting closer and closer to is what we're going to find with this formula here, where we use an infinite number of terms. Remember, the formula is the first term divided by 1 minus r. So our first term we already got is 3, divided by 1 minus the common ratio is 3/5. So that's 3 over 1 is the same as 5/5 minus 3/5. 3 divided by 5/5 minus 3/5 is 2/5. And that's 3 times dividing by 2/5 is the same as multiplying the reciprocal. 5/2. So we get 15/2. So that's what the sum of the infinite number of terms would approach 15/2. Okay, so the next one here, so we just found its sum right there. This one just happens to have pi and e in it. So again, let's find the first 3 terms, and then it'll help us see the common ratio. This time the starting number is 1, not 0. So we'd plug in 1, so it'd be pi over e to the 1 plus 1 is e squared. So there's your first term. And the second term, we call a sub 2, would be when you plug in the next integer after 1, 2. So it'd be pi squared over 2 plus 1 gives you 3, so e to the third. And then the third term, we multiply, if we plug in the next integer 3, it'd be pi cubed over 3 plus 1 gives you 4, e to the fourth. So here, looking at these 3, you can see the common ratio. The numerator is getting multiplied by pi, the denominator is getting multiplied by e, so it's pi over e. And so remember, this is approximately, pi is about 3.14, and e is approximately 2.71. So you can see in this case, that's bigger than 1. So that's not between -1 and 1, so this one diverges, which means it's just going to go to infinity in this case, get bigger and bigger and bigger, these terms. So we can't use this formula. This formula for the infinite sum only works if it converges, if the common ratio is between -1 and 1. Now let's take a look at the first 3 partial sums. So the first partial sum is just the first term, pi over e squared. And in this case, it's probably easier to just write out. And you could get a common denominator here, but it's not going to make it any simpler, really. So you could get pi over e squared plus, the second term is pi squared over e cubed. There's our second partial sum. And the third partial sum would be the sum of the first 3 terms. So pi over e squared plus pi squared over e cubed, and then our third term plus pi cubed over e to the fourth. And again, you could get a common number of e to the fourth here, but unlike these where we'll be able to combine them, it's just going to make it one single fraction that's not necessarily any simpler than this. So either way is fine. But those are our first 3 partial sums, and again on this one, you can't find the infinite sum, this last part, because the series diverges, it doesn't converge. And that concludes the notes for AP Calculus on the topic of infinite geometric series.